to daily physics. This is like John Stewart show, but not in politics, but in the physics. Okay. So this is Mr. Berry from Columbia University.
And this is Suborno Isaac Berry from NYU.
So today, Suborno, I have been thinking about a problem, and that problem has to do with friction. So you see the, can you imagine a pond? When you think of pond, who do you actually thinking of?
Poseidon.
No, Sir Isaac Newton. So a pond, because of cold weather, turned to ice. Absolutely ice. So a hockey puck, you hit it, okay? No, it's actually moving. Yeah, a hockey puck. Yeah, a hockey puck.
You just have to say like an ice rink. No one's playing hockey on a frozen lake.
Well, in Canada, that's what they do.
That's
what makes them great.
No, they build their own ice rinks.
Oh, really?
You know, it's very unsafe to play on frozen lakes. You know why?
Why?
Because ice rinks have like huge, thick layers of ice.
Okay.
Frozen lakes have 1 inch layer deep, which means if you step too hard, you can drown.
Okay, so the problem is the initial velocity, the hockey puck is moving with 20 meters per second, right?
Mm-hmm.
Final velocity is 0. From initial velocity to final velocity, it moved 120 meters. Wow, very nice.
Okay. So we have a hockey puck on this ice rink, and it's moving
20 meters per second
with an initial velocity of 20 meters per second, and it ends up coming to rest.
Who is responsible for slowing down?
Friction, of course.
Okay, great.
And it travels 180 meters?
120.
Okay, so here's what we have to...
What do you need to find?
Well, the...
mu k.
Mu k.
Yes.
Okay, so I'm actually going to approach this unconventionally using the Lagrange... using conservation of energy.
All right.
So, we don't care about potential energy.
What happened? Newtonian mechanics not going to be able to solve?
No, it is, but it's cool to do it in a separate way because everyone knows how to do it with Newtonian mechanics.
Okay.
So we have the initial kinetic energy, and then this plus the work done by friction is equal to the final kinetic energy. A version that makes more sense to a natural reader is subtracting the work done over... Wait, let me think about this. This would mean that the final kinetic energy is actually greater than the initial kinetic energy, which is obviously not true. You need to subtract on this side, or add on this side.
Am I allowed to say something?
What?
I wanted to say the velocity came from the kinetic energy, all right? The work done by kinetic energy is equal to work done by friction. Because friction ate up all the work.
I don't know about work being done by kinetic energy, but yeah, sure. So, kinetic energy final is 0, as you pointed out. So...
Oh yeah, that's what I was thinking.
Okay, now,
that's what I was
what
thinking.
do we have? We have initial kinetic energy is half mv squared. Work done by friction is just force of friction multiplied by the distance. So you get half mv squared is equal to the force of friction is just a normal force, which is equal to the gravitational force over here, unless we're on an incline, which I'm assuming we aren't. And then multiplied by this infamous man right here. So we have that multiplied by d. So we cancel it, which means it actually doesn't depend on the mass, which we weren't given anyway, so that's good. So mu k is equal to v squared over 2gd. Now v is 20. That's the initial velocity. We have 2. We're going to approximate acceleration due to gravity as 10 meters per second squared. And the distance that it traveled was 120 meters, which means that we have a factor of 20 on the top and the bottom, which we cancel out. And so that gives us a coefficient of friction of 1/6, which is about 0.167. And don't you dare ask me for units, because there are no units. That's what friction does. It takes away energy from the system and puts it into other things, mostly heat and also sound.
Convert sound energy to kinetic energy?
Sure you can. I mean, if you yell at like a feather, of course, the air coming out of your mouth is going to blow the feather away, I guess.